In chapter 12, the topic of light, we're going to look at reflection, refraction, and lenses. So please take a good look at these individual LOs, the learning outcomes that you must know to prepare for your exams. Let's look at reflection. Reflection refers to the change in direction of a wavefront at an interface between two different medium. So here we have medium 1 and medium 2, and the interface between medium 1 and medium 2. And we have an incident ray that comes from medium 1. It hits the interface at the point of incidence and is reflected back into the same medium 1. So that is reflection. So reflection refers to the change in direction of a wavefront at the interface between two different medium so that the wavefront returns into the medium from which it originated. So please be very careful when we look at the normal should always be described as the vertical line or the perpendicular line at the point of incidence. And the angle of incidence is always measured reference to the normal and the incident ray, and the angle of reflection is always the angle between the normal and the reflected ray. Now, the laws of reflection says that this angle of incidence is equal to the angle of reflection, and that the incident ray, reflected ray, and the normal at the point of incidence, they are all on the same plane. And the incident ray and the reflected ray are on opposite sides of the normal. Now, the image formed in a mirror is a virtual image. So a virtual image refers to an image that cannot be projected onto a screen. It is formed by divergent rays. So mirror image is also upright. It has the same magnification as the object. It has the same distance to mirror as the object, and it is laterally inverted. Let's look at reflection. Reflection refers to the change in direction of a wavefront at an interface between two different medium. So here we have medium 1 and medium 2 and the interface between medium 1 and medium 2. We have an incident light ray reaching the interface, and this light ray reflects and returns back into medium 1 from where it originated. So this is called reflection. Now, there are many terms that you need to be very familiar with. So for example, incident ray, reflected ray, the normal at the point of incidence, the angle of incidence between the normal and the incident ray, the angle of reflection between the normal and the reflected ray. Now, the laws of reflection states that this angle of incidence I is equal to the angle of reflection R, and that the incident ray, reflected ray, and the normal at the point of incidence are on the same plane. Now, it also says the incident ray and the reflected ray are at opposite ends of the normal. In a mirror, you can see an image. Now, the characteristics of that image is that the mirror image is a virtual image. It is upright. It has the same magnification. It has the same distance to the mirror as the object, and it is laterally inverted. Now, what do we mean by a virtual image? A virtual image cannot be projected onto a screen, and it is formed by divergent rays. Let's look at how to draw ray diagrams concerning reflection. So first, there is a mirror. There is an object. The first thing that you should do is to locate the position of the image behind the mirror. You can do that by the property of the distance of the image from the mirror is equals to the distance of the object from the mirror. So draw a perpendicular line, measure that distance, draw another perpendicular line, getting the same distance, then you can find image I. Then you draw the reflected rays from the image to the eye. So behind the mirror, dotted lines. Once at the mirror onwards, straight lines to the mirror, to the eye. Then you draw the incident ray from the object to the mirror at the points of incidence. Okay. And that's how we draw ray diagrams for reflection. Let's look at refraction. Refraction refers to the bending of light when light goes from one optical medium to another optical medium. So let's look at this example where light travels from air to a different medium such as water or glass. The light comes in at an angle of incidence of 0 degrees, and because the angle of incidence is 0 degrees, the light will pass straight through. There will not be any change in direction of light. If there is an angle of incidence, the light will bend towards the normal. The reason? The speed of light decreases because the light has traveled from an optically less dense medium, which is air, to the optically denser medium, such as water or glass. The angle of incidence is greater than 0, therefore the light refracts and bends towards the normal. Now, Snell's law states that sine, the refractive index n, is given by sine I, which is in air, divided by sine R, which is in the medium. Now, the refractive index can also be given by speed of light in vacuum, divided by the speed of light in the medium. Now, what happens when light travels from an optically denser medium, such as water or glass, to air? Now, if the angle of incidence is 0, same thing as before, the light will pass straight through. There will not be any change in direction of light because I equals to 0. Now, what happens when the angle of incidence is between 0 and critical angle? In this case, the light will refract. Refraction occurs, the speed of light will increase because the light is traveling from an optically denser medium to an optically less dense medium such as air. The angle of incidence is bigger than 0 but less than critical angle. The light will refract and bend away from the normal. Now, what is critical angle? Critical angle refers to the angle of incidence in the optically denser medium. So here, we are looking at this angle of incidence. This angle of incidence will give an angle of refraction of 90 degrees in the optically less dense medium. So in air, it will give this which is optically less dense, it will result in an angle of refraction of 90 degrees. So this angle of incidence is given a name called critical angle, and the formula is given by n equals to 1 over sine c. Now, why 1? Because sine 90 is 1. Alright. Now, what happens to a light ray with an angle of incidence bigger than critical angle? In such situations, total internal reflection occurs because the light is traveling from an optically denser medium to an optically less dense medium, which is air. The angle of incidence is bigger than critical angle, no refraction occurs, all the light experience total internal reflection. So the incident light will be reflected, giving I equals to R. Let's look at the laws of reflection. First law of refraction, for which is Snell's law, the ratio of the sine of the angle I to the sine of the angle R is a constant. So this refers to Snell's law. So for example, here we have medium 1 with refractive index 1, medium 2 with refractive index 2. We have an angle of incidence at medium 1, we have an angle of refraction at medium 2. This relationship is given by Snell's law, which states n1 sine I equals to n2 sine R. Now, refractive index can be defined as speed of light in vacuum over the speed of light in the medium, or sine I, which is in air, over sine R, which is always in the medium, or you can use 1 over sine C, with C being the critical angle, or you can use real depth over apparent depth. Now let's look at lenses. We are focusing on converging lens. So a lens is an optical medium with a curved surface, and there are 3 light rays that you need to be familiar with to know how the light rays travels through the lens. So the first one is if the light ray passes through the optical center of the lens, then the light ray will pass straight through without changing direction. The second light ray that you need to know how to do is if, let's say, there is a parallel light ray, these parallel light rays coming into the lens will converge to 1f, or the principal focus of the lens. Similarly, for the third light ray that you need to know how to do is if you have a light ray that passes through 1f and going to the lens, this light ray will then emerge parallel to the lens, to the principal focus. So using these 3 light rays, you can draw light rays and locate the position of the image. So giving you an example, if you have an object, you have the lens, you can draw any 2 light rays. So for example, I'm drawing the light ray passing through the optical center and the light ray parallel to the principal axis passing through 1f. These 2 light rays will tell me the position of the image, and in this case, this will be the image. Now, if you have a bigger object, a larger object, then you need to draw light rays from each corner of the image, or from the object. Okay, so in this case, I will draw these light rays to locate the image. Now, in your textbook and your notes, there are 6 cases, 6 different scenarios of how the lens can be used. Let's do some practice question. Question 1. Figure 1 shows a girl standing in front of a shop window made of thick glass. The front surface A of the glass and the back surface B are marked. She sees a reflection of her shoes in surface A. So this means we're going to use the mirror at A. On figure 1, draw a light ray from X reflected by surface A to the girl's eye. To do that, we need to draw the image of the girl, which is the same distance away from side A. So draw the image of the girl. Then we're going to draw a light ray from the toe, the image, to the girl's eyes. Alright. Then we're going to draw the light ray from the toe, which is the object, to the mirror at the point of incidence. Okay, so these 2 light rays will then answer question A. On figure 1, draw the angle of incidence of the light ray at surface A. Label this angle I. To do that, we need to draw the normal first, the normal at the point of incidence, then we can draw the angle of incidence. So draw the normal and draw the angle and label the angle I. Okay, you must label the angle I as stated in the question. State what is meant by the angle of incidence. The angle of incidence refers to the angle between the incident ray and its normal at the point of incidence. Now, many students will not mention the normal at the point of incidence, and you have to mention that it is a normal at a particular point of incidence. Let's look at question 2. A mirror is placed in the path of a ray of light. Determine the angle through which the direction of the light ray changed. So to do this, we need to find out what is the original direction of the light ray and where is the reflected ray, and then we can determine the angle between the original direction and the reflected ray. So this is the original direction of the light ray. This is the reflected ray, and we're going to look at this angle. Right, so this refers to the angle to which the direction of light has changed. Let's look at question 3. The diagram shows an object O viewed using two mirrors. A person looks into the mirror as shown. At which position is the image O seen? So this is a typical periscope. So to do this type of questions, you need to know that where are the mirrors. You can extend the mirrors and you can find where are the image, and the image of one mirror can become the object of a second mirror. So let's look at the first mirror. The first mirror is closer to the top, nearer to the object. So extend the first mirror, then draw the image of O based on this mirror. So here we get O to become O1, which is the image. Then we're going to extend the second mirror and we're going to draw the image of O1 based on this mirror. And so as you can see, that image is at position D. Question 4. Question 4 shows the plan view of a fish tank containing one goldfish. A boy sees two images of the fish when he looks from the position shown. Figure 5 shows a ray of light from the fish that is refracted at side B of the tank. The light ray enters the eye as shown. Draw a second ray from the fish to the eye that is refracted at side A of the tank. So, when light travels from the fish to side A, light will refract and bend away from the normal. So light ray from the fish reaches side A, it will bend away and enters the eye. Part B of the question shows the position of the two images of the fish. To do that, you need to trace the light ray backwards, and the position of the image will be nearer to either side A or side B. This has to do with the real depth and the apparent depth due to the refractive index of water. So, trace the light rays backwards and draw the image of the fish nearer to side A and nearer to side B. Let's look at question 5. The speed of light in different media or different materials is shown. So in air, water, and glass. Alright, calculate the refractive index of water and glass. The refractive index N is given by the speed of light in vacuum over the speed of light in the medium. So for refractive index of water, it will just be 3 over 2.3, which will give you 1.3. And refractive index of glass will just be 3 over 2, which will give 1.5. Now the answer here are given to 2SF because the speed of light is given to 2SF over here. So the refractive index is also stated to 2SF. And here you can see that glass is optically denser than water. So in each case, suggest and explain what happens to light as it passes from one medium to another, and complete the path of the light ray and explain. So let's look at the first case where the light ray travels from air into glass. So air is optically less dense while glass is optically denser. So the light will come into the glass, will refract into the glass and bend towards the normal. Explanation: light is traveling from optically less dense medium air to optically denser medium glass. The speed of light decreases, so light refracts and bends towards the normal. Now, what happens when the light ray travels from water to air? So in this case, water is optically denser, air is optically less dense. So the light will refract and bend away from the normal. In explaining this, the light is traveling from an optically denser medium, water, to optically less dense medium, air. So the speed of light will increase. The light refracts and bends away from the normal. Now, what happens when the light goes from water into glass? Again, water is optically less dense and glass is optically denser. So, like in the first case, the light ray will bend towards the normal, and the explanation will be the same as the first case, where the light is traveling from the optically less dense medium, water, to the optically denser medium, glass. So the speed of light will decrease, light refracts and bends towards the normal. In question 6, the refractive index of glass in air for light is given as 1.60. Calculate the critical angle, and using the formula n equals to 1 over sine c equals to 1.6, you can calculate the critical angle as 38.7 degrees, or you can leave the answer as 39 degrees. Both answers are accepted. In part B of the question, the light is incident on face Ln of a glass prism. The angle of incidence on face Ln is 30 degrees. The light enters the glass and is incident on the face Lm at an angle of x. Okay. Calculate the angle of refraction R. So this is a straightforward case of using Snell's law, where refractive index equals to sine I over sine C. So in this case, 1.60 equals sine 30 over sine R, giving R as 18.2 degrees. Or you can leave your answer as 18 degrees to 2SF. Now, in part 2 of the question, angle R and X are related by R plus X equals to 45 degrees. So what happens to the light? So angle X in this case will be 45 minus R, and that will give 26.8 degrees Celsius, 26.8 degrees. Now 26.8 degrees is less than the critical angle of the glass that we have calculated in part A. Therefore, refraction will happen, and because the light is traveling from the optically denser medium glass to optically less dense medium air, the speed of light will increase and the light will refract and bends away from the normal. The prism is now rotated so that the light is incident normally on face Ln. Explain why the light emerges from the prism along face Ln. Alright, so in this case, the light is incident normally, that means it's incident at a 90 degrees to the face Ln. This means the angle of incidence is 0 degrees. Okay, and because of that, because the angle of incidence is 0 degrees, the light ray will travel straight and does not deflect. When it reaches B, the angle of incidence is 45 degrees, and this angle of incidence is greater than the critical angle, and the light is traveling from the optically denser medium glass towards the optical less dense medium air. As such, total internal reflection occurs. The light does not emerge into the air. So that will be how the light rays emerges from the prism along face Ln. Diamond has a refractive index of 2.13, suggests why more internal reflection occurs inside a diamond crystal than in a piece of glass of the same shape. Now, internal reflections has to do with critical angle. So let's calculate the critical angle of the diamond, and from using the formula, the critical angle of the diamond is 28 degrees. What this means is that total internal reflection will occur if angles of incidence are greater than critical angle. So for diamond, any light rays with angles I from 28 to 90 degrees will experience total internal reflection. But for glass, which we calculated earlier, any light rays with I from 38.7 to 90 degrees will experience total internal reflection. So as such, there will be more total internal reflections occurring in diamond. And that's why diamonds are so sparkly. Yeah. Let's look at question 7. There is an air bubble in water. There are 3 light rays that are incident on the air bubble. Light ray 1, the angle of incidence is greater than critical angle. Light ray 2, the angle of incidence is less than the critical angle. And light ray 3 is perpendicular to the surface of the bubble. Part A. At the point where ray 1 meets the air bubble, mark the normal to the surface and the angle of incidence. So it is a property of a circle. If you draw a line from the center of the circle out towards the edge of the circle, that line is the perpendicular line to the center of the circle. So first line, draw the normal out, then indicate the center, the angle of incidence. Now, the angle of incidence is greater than critical angle for light ray number 1. So what happens is that the light ray is traveling from the optically denser water to the optically less dense air. So total internal reflection will happen. Okay, so the light ray will experience total internal reflection and reflects back into water. It will not go into the air. Now light ray 2, the angle of incidence is less than critical angle. Refraction occurs and because it is going from an optically denser medium to optically less dense medium, it will bend away from the normal. So with the normal, the light ray will bend away from the normal. Light ray 3 is perpendicular to the surface, which means the angle of incidence is 0. So there will not be any change in the direction of the light ray 3. And it passes straight. Let's look at question 8. Question 8 shows light rays traveling in water from a light source O. State what is meant by critical angle and mark the critical angle and label it C. Now, critical angle, as we have defined earlier, refers to the angle of incidence in the optically denser medium, and this angle of incidence will give an angle of refraction of 90 degrees in the optically less dense medium. So let's look at light ray B. This angle of incidence in the optically denser medium, it gives an angle of refraction of 90 degrees in the optically less dense medium. So this angle will be the critical angle. So how do you calculate this critical angle? First, we have to find what is the refractive index. So we're going to use A, the 30 degrees here, and the 42 degrees here. We're going to find the refractive index of water. So remember, N equals to sine I over sine R, and I is always in air, so in this case it will be sine 42 divided by sine R. R is always in the medium, which is sine 30, giving us a refractive index of 1.338. From there, you can use the formula for critical angle with sine C equals to 1 over N. From there, you can find C as 48.4 degrees, or you can leave your answer as 48 degrees to 2SF. Let's look at question 9. Question 9 shows the position of an object and its image produced by a converging lens. The diagram is drawn full size or full scale. When you are told that the diagram is drawn full scale, then you must check what scale are you using. So here we are using this scale of 1 cm to 10 boxes. So draw a light ray to locate the position of the converging lens. So we're going to draw a light ray from the top of the arrow or top of the object to the image, and this light ray will tell us where is the center of the lens, and here it is given by this point, and from there we can draw the position of the lens. Okay, and to locate the principal focus of the lens, we will draw a light ray that is parallel to the principal axis. From there, it will go down to the image, and from there we can determine where is the principal focus of the lens. And from there, we can determine where is the focal length. The focal length refers to the distance from the optical center to the principal focus. So this refers to the focal length. So if you're asked to describe the characteristics of the image, then this image is real, it is inverted, and it is magnified. So if you look at the object covers two small boxes, while the image refers the size of the image is three small boxes. So the image is magnified. So in an application, it will be a projector. let's look at question 10. In question 10, we have an object that is placed in front of a thin converging lens. The position of the focal points are marked F. So we're going to draw light rays to determine the position of the image and mark the position of the image as I. So we'll start off with the first light ray from the object to the center of lens, passing straight without any change in direction. We're going to draw the parallel light ray. Then this light ray passing through 1F and moving straight. Okay, then we're going to trace the light rays backwards using dotted lines. When they intersect, that will be the image. And this image is traced as a dotted line. Okay, and the reason for this is that this is a virtual image. It is upright, it is magnified, and we use this in the magnifying glass. Now, this object is moved further away from the lens until the object is very far away. Describe the changes to the characteristics of the image. So going back to the question, so this object now is moved towards the left side, away from the lens. And how will the image change? So when the object is at 1F, the image will be at infinity. Image is virtual, upright, and magnified. When it is between 1F and 2F, the position of the image is more than 2F. Image is real, inverted, magnified. When object is more than 2F, image is between 1F and 2F. Image is real, inverted, diminished. When object is at infinity, image will be exactly 1F. It will be real, inverted, diminished. So to answer this question, you need to know the position and the type of image that you will get when the object is at different parts, different positions of the to the mirror, to the lens. You have to memorize this somehow. Okay, figure 11 is a scaled diagram of a converging lens, an object and a real image produced by the lens. There are 3 light rays drawn from the top of the object. Okay, state what is meant by a real image. So a real image can be projected onto a screen, and it is formed by converging rays. Define focal length. Focal length is the distance along the principal axis between the center of lens and the principal focus. Okay, part C, complete the figure 11.1 by drawing the 3 light rays until they meet at the image. So this is very straightforward. The 3 light rays will all converge at the top of the image. Now it is important that you indicate the direction of the light rays with the appropriate arrows. So in this case, where is the principal focus? It will be on the principal axis.